Professor Dusit Niato is a prominent academic currently serving as the chair professor in College of Computing and Data Science at NTU. Please welcome Professor Niato.
Thank you very much. So the next session is security to where we have two speakers. So let me please allow me to introduce the first speaker, Professor Salil Kanhere. So he is the professor at the School of Computer Science and Engineering in the University of New South Wales, Sydney, affiliated with the Cybersecurity Cooperative Research Center and the U of New South Wales Institute of Cybersecurity. His research interests cover cybersecurity, IoT, cyber-physical system, blockchain, and machine learning. He has published more than 350 peer-reviewed articles and lead several government and industry-funded projects. Professor Salil is a ACM Distinguished Member and IEEE Senior Member. So he won so many awards, and he is the editor-in-chief of Ad Hoc Network and visited position in many universities. So he served organizing committees of several IEEE ACM International Conference and co-author of 2 books on blockchain technology. Without further delay, please welcome Professor Salil for the talk. Thank you very much.
Thanks. Thanks, Tao, for the very nice introduction, and thanks everyone to the organizers for having me. And it's good to see a crowd here on a Saturday. I was just telling someone if I had organized something in Sydney on a Saturday, it would be hard to get people in. So this work that I'll present is some of the work we've been doing in our team around decentralized identity. Luckily, no one talked about it much. I think Professor Lau probably mentioned it yesterday in a talk, but at least I'm not overlapping with any other people. Okay.
Could you try this one?
Okay. Yeah, thank you. Thank you. Oh. Okay. So, as you all know, we are pretty familiar with physical identity, right? All of us carry various forms of identifiers, and when required, we always show them, and the people examining them will hopefully trust what you're showing them. If you walk into a bar, depending on the drinking age in your country, they will check your birth date. It doesn't happen to me much often now, but it used to in the past, right? That works. However, when it comes to digital identity, I'm sure you will agree with me that we haven't yet solved the problem, right? So this is a very classical picture I often show in my networks class as a reminder to how the internet was conceived, right? The idea was the internet, everyone is sort of private on the internet, nobody would know who you are. However, in reality, things are very different because a lot of us are leaving various digital footprints all around. And if someone really wanted to track you, it's not very hard to do that, right? There are various real-world examples of this happening. So, of course, those are 2 extreme cases. We are kind of somewhere in the middle, I would say. So, of course, as users, we are very concerned about who has access to our data, personally identifiable data. And at the other end, if you also look at these service providers, it's also challenging for them, right? If you think about it, if it's a bank, for example, they want to make sure their services are not being used for money laundering and other nefarious activities. So it's been a struggle. And if you look at where we are currently, I mean, we've all kind of familiar with this centralized approach of identity management. So each time you want to access a service, you create a particular account with them, and then you have to manage your passwords and so on. And as we clearly know, this model has a lot of problems, right? We have seen many examples of people's personal information being exploited because this central authority got hacked, right? Numerous examples around the world. Then there's been this other approach of federation, where you kind of don't necessarily set up individual accounts with the service providers. you rely on certain entities, and you see the popular ones up there, Meta, Apple, and so on, Google. And you essentially rely on them to provide an authentication token to the particular service you want to use, so that they then recognize the authentication token from these providers and let you use their services. Now, this is great in that we don't need to create individual accounts. The problem here, of course, as you may appreciate, is you're relying on these service providers and you do not necessarily know what they're using this data for, right? If you use Facebook each time to log in to various services, then Facebook will know what services you're using. And then it's up to you. I mean, it really depends on how much trust you place into Facebook for storing and managing that information. So before we proceed, just a quick reminder here by identity. I'm kind of broadly referring to this whole, what's referred to as a credential in this space. So a credential is essentially some information that a particular issuer can verify about you, right? So you're all, familiar with various forms of credentials like licenses, certificates, student cards, and so on, right? Now, of course, in the digital space, we are looking at a digital representation of this, and I know many countries are doing this. For example, in Australia now we have a digital license that I can carry, so I don't actually need to carry my physical license. So in this ecosystem, you have three players, essentially. You have the issuer that is issuing the credential. You have the holder, that's the person that obtains the credential and wants to use it for various purposes. And then you have the verifier, which is a particular service provider that wants to confirm that this is the appropriate individual so that they can provide the expected service, right? For example. Now, of course, in the digital space, we want to do this in a remote manner. Essentially, all of this has to be managed digitally. It has to be tamper-proof. It has to be trustworthy. And it should be very easy to create these presentations, as they're called, as required, right? So we've been struggling with this. We still see this sort of hacks happening all the time. For example, last year we had 3 major hacks in Australia. A lot of personal information was revealed. People had to change their driver's license, so it was quite onerous. We are talking of millions of people, right? So there are various problems with this, as you see there. And what's missing is essentially a way whereby we take ownership. We have more control over these credentials, just like we have control on the physical credentials. We want to have a similar sort of conception on digital credentials, right? And some other factors that you see here. So there's been this push on this notion called decentralized identity or self-sovereign identity, as it's called. Christopher Allen is largely credited with pushing this, right? And as it says here, there are 2 aspects to this. So one is, of course, the whole ideology, which I won't get into here. But then the architecture to mobilize this sort of digital identity infrastructure is something that we've been working on in our group. So Christopher Allen, he proposed these sort of 10 key principles, as you see there. I won't walk through each one of them here for the sake of time, but you see some of these kind of make sense in a way. You want transparency, you want persistence, you want portability, you want things like minimization, which is quite important, particularly when you're revealing things. You want to only reveal information that is absolutely necessary for that particular service. Right? So in this particular context, this is sort of a quick high-level overview of what a DID stands for. So it's basically just a unique identifier, as you see up there. There's something called a scheme, there's a DID method, and then there's an alphanumeric number, right? So this is unique, this is permanent, resolvable, and each time you create a DID, you're also creating a public-private key pair, which allows someone to verify this DID. And the whole notion is that this should be decentralized, so it's not under the control of one particular entity. As you see here, you have what's referred to as a DID URL that points to a DID document, which contains some meta information, including the verification keys. And this is where blockchain comes in, essentially. All this information is normally stored on a registry, and it's not necessary it has to be a blockchain, but a blockchain has been proposed as a very convenient repository for that particular information, where you store all the registry information. So how do we use this? Well, it's straightforward, kind of captured here in this picture. So the issuer will issue a particular credential for the particular holder. The issuers are, of course, well known. They publish their DIDs on the ledger, so anyone can check that who the issuer is and confirm. What's not shown here is the holder would also normally put their DID on this ledger. So anyone can first confirm when they receive a credential, they can actually confirm that this is the right person, right? So that's not captured in this picture. But then the verifier will request for a particular proof, depending on what service is being accessed, say age, for example, right? The holder will create this proof, show it to the verifier. The verifier will confirm using the ledger, check the DIDs for both entities, and as long as the signatures match, they will be satisfied that this is the right verified credential. So we've been looking at this ecosystem for some time. What I'll do is I'll present to you two pieces of work that we've done in this space, just to give you a flavor of some of the issues involved. So this first one is a very classic one, which is essentially data minimization, right? And I'm pretty sure a lot of you have seen these sort of vaccine certificates, for example, in the past few years, right? So as you notice here, this is a vaccine certificate from Australia, and you see it's actually revealing a lot more than what is actually required for someone to check whether you have obtained the vaccine, right? For example, why does someone necessarily need to know the date of birth if you're just checking my vaccination, right? So things like that. In fact, there are other versions which even had addresses on them that we've seen, right? So this is a little older piece of work, but I think it's a nice representation. So here we were looking at how could we extend the DID ecosystem to allow for data minimization, right? So a simple example we use is, let's say you have obtained your certificate. It's a digital, a transcript. It's a digital representation of your transcript. And you want to selectively reveal certain parts of that transcript to different entities, right? So if one entity may simply need to know which university you went to, you necessarily do not need to reveal your GPA, date of birth, for example. Another entity may want to actually check your GPA, right? It might be a prospective employer. So what we need is a mechanism which can very efficiently allow the user, the holder, to create these presentations. Now back then we found certain signature schemes. The problem was each time you wanted to create this presentation, you would have to go back to the issuer and regenerate the credential. So that is kind of wasteful, right? So what we wanted was a mechanism whereby once the user has the credential, they can create these different forms of presentations, hiding certain attributes as they wished. Okay? So we looked at what's available in the literature, and we found one particular mechanism that could do this, and this is based on the GGM structure that you see here. I might just very quickly go over this. I don't want to go too deep on the technical aspects, but as you see very clearly, this is a standard Merkle tree structure, right? So the idea here is you start with a particular random seed, L epsilon, and you create this random numbers at each node as you go down the tree. So that's the first expansion phase. Then down here, the leaf, the children at the bottom, so these are the actual attributes within your credential. So for example, date of birth, GPA, and so on, right? And then you hash like you normally do with a Merkle tree up the tree, and you create, you have the root, which is then signed. And what we create at the top is what's called an extensible signature. Oh, sorry. Right. So in order to use this, these are the 4 simple steps that need to happen. So there's a setup phase. Essentially, the issuer sets up some of these parameters and keys necessary for this process. The issuer can also mandate that certain fields cannot be hidden. Okay, so we have the flexibility. So if it's a university, for example, it may say you cannot hide that this degree comes from NTU, for example, right? So certain fields could be mandated to not be removed. So that's referred to as RDT up there. And then the issuer would create the signature as per the previous slide I showed you. Create the credential, sign the credential, and put this on the ledger. Once the holder has the credential and they want to sort of hide certain attributes, so these are represented as RM. Now, of course, any attribute in RM cannot belong to RDT. That would fail. This step would fail. Assuming that doesn't happen, when the issuer is actually redacting certain attributes, those attributes are not included in this computation. Instead, the hashes of those attributes are added to the extensible signature. So you're not revealing the actual attributes, but you're revealing the hashes of the attributes in the extensible signature. And later, once this credential is presented to a verifier, so let's C prime in this case, along with the new signature, the verifier can reconstruct this because they have the hashes and they know which particular indexes those attributes belong to. So even though they do not know the attributes, they have the hashes, so they can recompute this and verify that the signature matches. So that's the key idea here. So what we did was we implemented this within an SSI ecosystem. So here you'll notice at the top there's a DApp server that all the entities use to communicate with the backend. Within the SSI platform, you have standard services to create accounts, to create DIDs, issuer services. And then down here, you have the actual registries that are stored on the chain. And you can have smart contracts managing that. And at the top, you notice the credential services that we've added. So those are the actual functions. So you have the SDA part, and then you have the verification part up there. Now we implemented all this, and we've built a proof of concept. It all works. I don't want to show you some of these numbers. I think I'll run out of time on this, so I'll skip some of this. But you can look up the paper for that. So that's one part, essentially. The fact that you can do this data minimization on the fly without having to go back to the issuer. The second part of this talk, I'm going to talk a little bit about this trust relationship, right? So the issuer is there in that triangle. As we saw there, the issuer creates the verifiable credential. The holder presents that, and then the verifier checks, confirms the signatures, and is then satisfied, right? Now, one key thing there is the verifier has to have some trust in the issuer, right? So if you get a transcript and it says it's from NTU, right? If you're a person hiring that particular person, you would probably trust that, okay, yeah, NTU, it's a valid institute, so I trust this particular transcript, right? So that's all fine, but if you look at the SSI philosophy, the idea there was to also allow us individuals to create credentials on the fly. So for example, you want to give a letter of authority to your next of kin, right? Or if you're going through a medical emergency and you want to allow your friend, say, to take action on behalf of you because you're incapable, right? So some of these decisions might have to be made on the fly, and we as individuals should be allowed to issue credentials to other individuals for certain specific purposes, right? Now the problem is, if you look at the SSI ecosystem, the issuers have to go through heaps of mechanisms to be able to actually issue credentials. So there's this very complex and elongated onboarding process that the issuers have to go through in order to issue credentials, right? However, that's too cumbersome for each individual to go through that process, right? So in this work, what we are trying to do is coming up with a onboarding process whereby someone who's trustworthy can quickly onboard someone else to be able to give that person authority to issue credentials and allow them to essentially create personal credentials on the fly, right? So that's sort of the big picture of this work. So this was presented last year, and the example we use here is shown on that slide, right? So let's say we have a particular person, Anna. She's got an accident, and her friend Tim takes her to the hospital, and she wants to give Tim authority to take certain decisions for a treatment because she is not capable to do that because of whatever she's experienced, right? So the idea would be we create mechanisms within the SSI ecosystem for Anna to create essentially a letter of authority, giving authority to Tim to take medical decisions on her behalf. So later, when Tim presents this to, say, the treating doctor, say a physiotherapist, the physiotherapist can quickly verify that, yes, this is the right person, and Anna had actually given this person the authority to take decisions on her behalf. And we want all this to happen within the SSI ecosystem in a transparent manner. So how do we do this? So in this, we go back to our classical learnings from the internet, and you might be aware of the web of trust, right? So the same idea is what we are trying to capture here, where you have what we call the top level or level 1 issuers who are sort of onboarded through this complex process, and they can create these supporting credentials and allow other individuals, say like a doctor, to onboard one of their patients to take certain decisions, which is captured here, right? And this sort of chain of trust can go further deep if you really wanted to. We're just going to use 3 levels in these examples, right? Sometimes you might even want multiple people to have endorsement. So you have the flexibility to define how this trust propagation actually happens, who has the rights to onboard individuals, and so on. So to allow that, there's the notion of what we call a template, a propagation template. So it's quite similar to any forms that you see on any government website, right? So you create this template. This template will specify certain rules for usage. It will indicate who can onboard, what roles those individuals should have to onboard others, and so on, right? And this template will then be sealed. It will be signed at that point, right? So this is an example. Hope it's clear. So this is capturing a letter of authority, essentially, issued by a particular individual. Going back to that same example, actually, a patient has issued a letter of authority to one of their friends. So you'll notice this credential actually contains that trust propagation template in there. And this template has various forms of information, including a policy on who can serve as the proxy. So up there you'll see that a doctor belonging to a particular hospital can serve as the proxy, and what permissions can they actually give to the next level, to the actual individual down there. Then here you'll notice the actual trust proxy, which is doing the onboarding process, and then finally the actual credential down here. Now one thing to note is this trust propagation template is actually signed and sealed, right? So what we need is a mechanism, because when we create these templates, we do not know who these individuals are, right? So we cannot add their names at the time of creation of the templates. So we need cryptographic primitives which will allow you to add those information at a later point in time without necessarily breaking the validity of that whole template, right? So we need something whereby you can go in and change certain sections of that template on the fly. Okay, so this is where we found a particular mechanism called sanitizable signatures and chameleon hashes, right? So if you know of chameleon, I mean, this has been used in other contexts in the blockchain ecosystem, but not for this particular application. So when you apply a chameleon hash, essentially you can specify a certain sanitizer. Essentially there's a trapdoor, and if you have access to that trapdoor, you can actually go and change the actual text because you can then find a different nonce which essentially will create a collision in the domain of the function. So essentially your hash can stay the same, but you can go and change the underlying text, okay? Assuming you have that backdoor. Okay. Now in this case, managing those trapdoor keys is kind of super important. So in the context of our use case, we said, okay, we want certain specific entities to be able to do the onboarding. So what we'll do is we'll encode this using an attribute-based encryption scheme. And if that particular person has those attributes, for example, you could say only a doctor belonging to hospital X can do the onboarding, right? For patients that belong to that hospital. So the doctor would then have to prove that they have the appropriate attributes to be able to get access to that particular trapdoor key, and then they can go in and update the particular sections. So this is the big sort of overview of the whole mechanism. So you have 4 phases, as you see there. The first up there is basic, just the setup. You set up the access attributes and the public and private hashing key, and then a master key for each attribute. Then you have the actual template creation phase. So you have the template. You then indicate which sections you're going to allow to update. And you have a chameleon hash and a matching trapdoor for each of those sections. Then you sign the template hash and you store that particular credential onto the chain. Both the hash credential and the signature. Then at a later time, let's say the doctor wants to onboard the patient, Anna. The doctor will need to have access to this template, of course. They will need to have access to the trapdoor because they want to change certain sections in that template. In order to do that, they need to prove that they have the appropriate attributes. So they need to prove that they are a doctor in that particular hospital. So they would contact the access attribute generator, show the proof, essentially just another credential indicating they are a doctor in that hospital. That would give them access to the trapdoor key. And they would then go ahead and update the particular sections they need to. They would sign the updated template hash, and then the hash and the signature could be then stored again on the ledger. Now there's one other check we've added here. So yes, all of this will make sense as long as the protocol holds. However, this doesn't solve potential collusion, right? What if I'm a doctor and I want to onboard someone who's my friend or whatever, right? For nefarious reasons, right? So how do we prevent that? How do we prevent collusion in this? So to do that, we've also added an optional voting mechanism, which would actually require other members in that particular organization. So let's say, again, other nurses or other doctors in that particular hospital to verify that the person being onboarded is the right entity and for the right purpose. So there's an optional voting mechanism that can also be initiated through the template. Okay. At a later time, once someone has access to the updated template and they want to verify that this is, so let's say they've got the letter of authority and they want to verify the letter of authority. They have access to the hash and the signed hash. So they would then initiate a verification function which would pull out the information from the ledger, and they would confirm that the signatures actually match. So this will also confirm that the template is correct and that Anna has the appropriate authority to issue the letter of authority. So this is the voting mechanism I was referring to. So this has kind of two steps. So there's one setup phase right at the start where the system administrator would deploy the voting contract. The voting contract would contain details of how many votes are required, what kind of individuals can vote. And then later, during the actual, during that particular step, the second step when the template is being used, if voting is required, then a vote request goes to the system administrator. The system administrator has already onboarded all the voters. They've set up all the keys to manage the voting. So at that time, this particular sections would be shown to the voters. They would have to confirm that that particular person is the right person to be onboarded. Whatever the voting mechanism entails would have to be checked by those particular voters, and then their vote gets sent to the contract, and the contract outcome will determine if the vote passes. And only if the vote passes would the updated credential be added to the chain. Again, in this work, we've actually gone ahead and implemented all of this within an SSI ecosystem. So essentially adding on to the previous work. We've used this particular example, the same example I talked about, essentially a doctor onboarding a patient, right? So there are two steps here. First is onboarding of the doctor as a trust proxy, and the second step is onboarding the patient to allow them to issue credentials to their relatives, right? Again, I'll skip the graphs here. They're not super interesting. The point here was to show that all of this works, right? So we were able to show that all of this works very efficiently. The signatures executions takes a matter of few seconds at most. And you can run this on a very basic blockchain network with sufficient throughput, essentially, right? So there's lots to be done here. So all of this trust basically has to be very domain specific, is what we say, what we have found out, right? So this will be very specific to each vertical that is adopting this, right? So certain things that work in a hospital may not necessarily work in a university, may not necessarily work in the finance domain. So I think a lot needs to be done to unpack this and look at how do you set up the governance for these different verticals and how do you actually move forward with this transfer of trust, as we call it here. And more broadly, within the SSI ecosystem, again, there's lots of work to be done. Most of the big players have signed on. There's various implementations of SSI that you can find there. There's various startups, some of them we are working with in Sydney, exploring this. There's also standardization. There's W3C standards on SSI, on DIDs in general. So yeah, it's a very interesting space, and if you're interested, do have a look into this, some of our work and work from others. So I think I'll leave it at that, and hopefully I'm on time. Thanks.
Thank you very much, Salil. Very interesting talk, decentralized credential, and due to the time limit, we have one question maybe. Please, if you have any question from the audience. Oh yes, please.
Yeah, I have two questions. So the first one is, because now you depend on DID ecosystem only, so there's no CA to issue the certificate like traditional PKI. So how can you make sure that the organization that registers its DID on chain is true? For example, if UNSW registers a DID on blockchain, and I also register a DID and claim that I'm UNSW. So who can trust which one is true?
Yeah, good point, good question. So the question pertains to the level 1 issuers, right? So as you said, UNSW creates credentials, and what if someone else also claims to be UNSW? So this is what I was talking about. If you're a level 1 issuer, there is a lot of it's quite a laborious process to actually onboard yourself onto the ecosystem, right? So it's not easy for someone to just say, okay, I'm a university, I want to offer credentials. You would have to go through a lot of checks, right? So I think it would be very hard to get in as a fake level 1 issuer, right? Now, under that structure, so this is where I was referring to, within each domain, right? So within UNSW, I can then set up mechanisms to onboard other people. And that's where UNSW would have to make sure the trust templates are set up correctly to prevent someone sort of setting up false credentials under that umbrella.
I see. Okay. So the other question is, because you mentioned redactable signature, and but for example, in Europe, they have an EID regulation, and they said the user should not be traceable. That means the signature should be unlinkable. So with this kind of redactable signature, can you achieve this kind of unlinkability?
Yeah, so yeah, the question of unlinkability, that's a challenging one. So yes, with this scheme, you're right, we do not satisfy that. So there have been, we are looking at some other schemes essentially to address this, but fair point, yep.
Okay, thank you.
Thank you very much. And again, so the speaker will be around in the workshop. So please feel free to ask the question. So thank you very much again. And we move to the next speaker.